Hello and good morning everyone. Welcome you all for the NPTEL online course on economic operation and control of power systems. So we'll discuss state estimation. So let's say there are few samples have been given to you. We need to estimate the states, that is A and B, right? So states are those variable, by knowing them you can know the unknown things, right? So we can express output variable as a function of state variable and the input variable, right? Y is equal to Ax plus B. So the measured value of the samples are given by Z. This is the actual measured value. Now you are trying to estimate the states of that measured value actually, right? So this can be expressed using a curve fit formula. F of x is equal to Ax plus B. That is what is output that you need to find it out. So this is depending upon the state variables A and B and the input variable x, right. So the objective is to obtain that specific curve fitting function which will be able to estimate the states of the given measurement. So the error, obviously there will be error, no, the error is the difference between the measured value and the estimated value, which is a function of state variables, right. So E1 is equal to Z1 minus Ax1 plus B and E2 is equal to Z2 minus Ax2 plus B. Now the objective is what? To minimize the error, because error could be negative and positive. So henceforth, in order to avoid that, what we are doing is error square. So even though if there is a negative, so we will make it as a positive. So that means minimizing this actual measurement and the estimated measurement, estimated value. So in matrix form, if you want to represent it, error matrix is nothing but the measured matrix minus this H matrix, we call it as H matrix. So function matrix basically x11, x21, xm up to 1, no, into this state variable matrix. These are the matrix, this is the matrix that you need to find out, A and B, right. So or you can express epsilon or error matrix is equal to Z minus H into S, right. Now the objective is to minimize this error, right, or minimize the this matrix Z, which is the actual measurement, and this estimated matrix Ax plus B, right. Now what is this? This can be in mathematics form expressed as Et into E, transpose matrix into E, because the square matrix. So in matrix form you can express this as Et into E. So Et, what is E? We know Z minus Hs. Now find out what is Et into E. That means Zt minus this matrix whole transpose into the matrix, right. So if you have to minimize Et into E, so you will have to minimize this whole matrix, right. You just multiply it, multiply 1 to 1. So you will get this term. Now minimizing means the differential equation, right, you need to differentiate and that should be equal to 0, right. So gradient of this, that should be equal to 0. Now you differentiate with respect to yes. Now what you will get? This is a constant term Zt into Z, because that is a measurement value which you are getting, it is a constant term. So this is anyway constant, derivation will be 0. Now you have to differentiate these two terms with respect to S. Now what you will get? Minus Z2 into Zt into H, because dou S by dou S is 1, plus this is what? St into S, this is nothing but S square basically, right. So what you will get? 2 into S basically when you differentiate, that is nothing but 2 into Ht into H into S. Now this is equal to 0, right. If you make this as 0, what you will get? Minus 2 Htz plus 2 Ht Hs is equal to 0, right. You need to find out S basically. S means 2 Htz multiply by Ht into H whole inverse. This is what we have done. Of course 2 gets cancelled, you will ultimately get Ht into H whole inverse into Htz. This is what you will get. That is a state matrix that you are going to find out. you know what is the measurement matrix, actual matrix with the, because you are getting samples, you know what is Z. Having known this model function matrix which is having these variables x1 x2 and all these parameters, so then you have to do this mathematics only, H3 H inverse H into H transpose, and you will get the state variable matrix, right. Now perform an example, perform linear regression on 1, 1.5, 2.8, 3, 2.2. Here 1.5, 0.8, 2.2 are the measured values. So that is why we have kept it in as a Z matrix, and remaining you have the H matrix. Now, this measurement is taken for a specific function and that value is considered as 1. So this measurement is taken at a specific condition where that value of that function matrix is 2, similarly 3. So the function matrix you get is H is equal to 1 1 2 1 3 1. Now you do it H3 into H and then H3 H inverse H3 into Z, then you will get the state matrix, that is 0.35 0.8. So basically for this sort of measurement the state variable is 0.358. By knowing 0.358 and having different value of 1 2 H matrix, you can find out the value of Y, which should be ultimately closer to the Z matrix, the measurement matrix basically. So let us find out maximum likelihood estimator. So the objective is to minimize this. What is this? This is a measurement value, this is average, this is standard deviation, right. This need to be minimized. So we have discussed in greater detail about Gaussian matrix and how the data should be closely present with respect to the true value, right. So where J is the objective function to be minimized, we now define a quantity called the measurement residual Ri for the ith measurement as shown below. This residual value for this Z measurement at the ith sample, at the ith measurement. So that is nothing but the difference. So this is the actual measurement, this is the average. So average is nothing but expectation of Z, where EZi is the expected value of the measurement Zi, right. Notice that the expected value of Zi can be determined from the equations or functions of the measurements in terms of the system states. The expected value of Z can be obtained from the system states. So basically this is what the measurement matrix and this is expectation matrix. So expected value should be close to the true value, right. That means you want residual item should be 0, that will be the objective. The error, this is basically error. So for example, power flow measurement at a bus can be determined from the power flow equation given the values of the bus voltage, magnitude and angles. Here bus voltage and angle, they are the state variables, correct. So let us say you need to find out power flow, that P is nothing but, we know this way, Vi, Vj, Yij cosine of theta I minus theta j minus alpha ij, right. Similarly reactive power flow is Vi, Vj, Yij sine of theta I minus theta j minus alpha ij. So power flow is depending upon voltage magnitudes and the phase angles, whether active or reactive power. So these are the state variables here, and it also depend upon transmission line parameters. Here that is been taken care by this Y matrix, correct. Having known this voltage magnitude, phase angle and this transmission line parameters, you would be able to find out what is the line flow, right. Now let us now define the weight assigned to the ith measurement as Wi is equal to 1 by sigma I square, right. So above means that the measurement that have higher variances are assigned less weights. That means you are getting a measured value and that is too much deviated from the true value, actually has lot of variances, that is what the standard deviation identifies as. Now if you have the data which is far away from the standard value of actual measurement, so that for that specific measurement we are giving very less weightage. That means you do not want a specific measurement to have a lot of deviation or variance. So this weight matrix is very important. So the problem of determining the maximum likelihood estimates then becomes the following. So this is the minimize, this is the function that you need to minimize, subject to zi is equal to hif(x) plus ei. What is hi? This is a measurement function for the ith measurement, x is the vector, that means we are assuming that there is a measurement and it may have some error. This h of x is the true actual measurement. The objective is to find out that h of x now. The measurement has some error, and that error we are assuming that there will be that error and there will be some true value also, right. So we are trying to find out the true value. Now x is the vector of the system states, because and that depends upon the system states, actual value depends upon the system states basically, consisting of bus voltage magnitude and phase angles, and E is the vector of measurement errors, correct. Above formulation for the state estimation is the so called weighted least square state estimation problem. Now the ith measurement Zi is modeled as given below, expressing all the measurements in a compact form. Now just express in the matrix form. This is the measurement matrix, that is equal to h of x plus error, where h is the vector of measurement functions of the measurement vector z. Following assumptions are taken regarding the statistical properties of the measurements. Some of the assumptions. The first assumption is expectations of the measurement errors are 0. So ultimately, as a true system state estimator, I do not want any error to be present in my estimation. So the measurement value should have 0 error. So that means expectation of error, do you want to have high expectation? No, you should have minimum or 0 expectation. So expectation of the actual measurement with respect to average, that should be 0 for all the measurements, and measurement errors are independent. That means you are getting measurement from different devices, let us say, and they are independent, they have each measurement device may have its own error, and that error may not have dependency on another error, right, which is coming from some other measurement device, right. So basically what we are trying to find out is there any interdependency in error that is being populated from different measurement devices, that we are going to find out. So what we are saying is, let us say EI is a measurement taken from some measurement device, EJ is a measurement taken from other measurement device. So their dependency is 0 basically, that means EI into EJ, their expectation is 0. What we are saying is, if EI is there, maybe some value, true value, and multiply by EJ, which may be some other value, their covariance or their sort of dependency is 0. So based on the last equation, this so called error covariance matrix is defined as covariance of E is equal to expectation of E into E transpose. So that is nothing but diagonal matrix. Now this is a diagonal matrix. If there is any dependency in this matrix, the off diagonal elements will be non-zero. Now this is a dependency on the first error with respect to that measurement itself. This is a diagonal element. This is second measurement with that there will be dependency on that variable, that measurement with respect to that measurement itself. So this is second entry is that second measurement basically. But this diagonal entry, surely it will be non-zero matrix, non-zero entry, but off diagonal it will be 0 if there is no dependency on each measurement. Now this diagonal matrix, no, the entire covariance matrix, let us term it as R basically, right. Now assuming the measurement error to be independent, the error covariance matrix R mentioned in the last equation becomes a diagonal matrix with the inverse of the measurement variances as the diagonal elements, right. The non-diagonal elements are zeros basically. The ith diagonal element Rii of Ri is given by, now E, this is expectation EI into EI, because we are just looking at that specific measurement itself, that is E into Zi minus mu I into Zi minus mu I, and that is what Zi minus mu I whole square, that is expectation of this is nothing but the standard deviation. Now the objective function can then be written as g of x is equal to this matrix half into summation of I is equal to 1 to m Zi minus Hi of x divided by Rii. Rii is nothing but sigma I square, I am just replacing it. Now this can be split actually, square is multiplied as transpose into the actual matrix, right. So Zi minus h of x into whole transpose, what we are doing is 1 by Ri is R inverse and then multiply by this matrix again, Z minus h of x. This is just a mathematics adjustment, because transpose has, you should know, no, the multiplication should have a proper let us say 2 into 3 matrix, if you want to multiply, the other matrix should be size of 3 into 2, right, dimension should be matched actually. So now this is the function, objective function. In order for g of x to be minimum in the last equation, the following condition must be satisfied. Now you differentiate j of x with respect to x, right. So because we are minimizing it basically, so that means you have to differentiate the previous expression, you have to differentiate this j of x, you need to differentiate with respect to x. So what you would get, so z minus hi of x, you are differentiating this 1 by 2 into, first differentiate this matrix actually. So 2 into zi minus hi of x and 2 gets cancelled, and then you will get 1 zi minus hi of x divided by sigma square, r inverse is nothing but 1 by sigma square, right. So that multiplied by again, yeah, dou hi of x by dou x, because the inside term you are differentiating again, you understand, no? So you will get this matrix. Now it's some mathematical adjustment, this can be further deduced as minus ht into r inverse into z minus h of x. How? We are replacing dou hx by dou x by h, capital H. So this is replaced by, or this is nothing but z minus h of x again, you just keep it as it is, z minus h of x, 1 by sigma square is r inverse and dou h by dou x is h, but for mathematical adjustment we are making it as h transpose. So h minus h transpose into r inverse into z minus h of x. Now let us now find the Hessian matrix for the measurements, because it will be needed soon in our derivations. So Hessian matrix is the derivation of the previous matrix, that means dou by dou x of g of x, that is nothing but dou square by dou x of j of x, that means you are partially differentiating this g of x twice, double derivative. So you have to do the partial differentiation. How do you do it? Find out where is j of x. Yeah, this is your j of x matrix, this is your j of x matrix, you have to do the partial differentiation, that you will get as dou square j of x by dou x, you will get, there are two terms that you will get actually, 1 by sigma square which is r inverse, it is just this dou by dou x of u into v, you know this matrix and this multiplication, right, dou u by dou x into v plus dou v by dou x into u, right. So that is what we are doing here. So dou h of x by dou x, you just keep it as it is and then differentiate this again, this is nothing but dou h of x by dou x again divided by 1 by sigma square, and then minus 1 by sigma square, you keep this as it is, zi minus hi of x, and differentiate this again, that is dou squared by dou x square into h of x, because z is anyway constant, you need not have to differentiate that. So neglecting the second term, we are just ignoring the second term, what you will get, this is nothing but g of x is nothing but h transpose, this is h matrix, dou h by dou x is h matrix, h transpose into r inverse into h approximately. Above is called the gain matrix for weighted least square state estimator. This is the gain matrix. Now expanding the elements in the vector g of x in Taylor series. Now this is the general Taylor series expansion, right. So this is nothing but, let us say if you want to find out what is delta x of k, delta x of k is nothing but x of k plus 1 minus x of k, it is difference between the measurements. This is the state estimation matrix, right, state estimation matrix. So it's keep on updating at k plus 1 state estimation difference with the k state estimation, that is nothing but minus of g of x k, because this is 0, this is inverse into g of x k, right. So this is the increment in the state vector, or g x of k plus 1 minus x of k is nothing but this is what you get, minus g of x k whole inverse into g of x k. The iterative equation for weighted least square estimation therefore can be written as x of k plus 1 is equal to x of k, you just take x of k on the right hand side minus this term. Now x of k, now you replace g of x k by minus, we have got this value already, g of x nothing but minus htr inverse z of minus h of x, just replace that here, then you will get this term, right. But in order to find out the next iteration updated state estimation, this is x of k plus 1, you need to find out g of x k inverse. So that is a tedious job basically, gain matrix inverse, finding it every time, that is a tedious task, a computationally demanding task. So efficient numerical methods such as LU factorization, Cholesky factorization etc. are typically used to effectively invert the gain matrix. Some decomposition need to be done. The estimation process starts with the following equation, g of x of k into delta x k plus 1, this is nothing but delta x k plus 1 is nothing but j x k inverse, the same expression, we are just writing it like this, where delta x k plus 1 is equal to x of k plus 1 minus x of k. There are some set of procedure that you need to find out, follow. Steps for implementation, step number 1, start iteration, set iteration index k is equal to 0 and initialize the state vector x. Initialize the state vector means what, let us say for example power flow equation, even if you have remembered we discussed about Gauss-Seidel, Newton-Raphson and all, and I gave you an overview. So what we used to do, we used to go start with a flat start, right. So those buses where we do not know voltage and phase angle, we used to assume voltage as 1 per unit and phase angle as 0 degree, right. So that is what we are starting here. Initialize the state vector matrix x, typically all the bus voltage magnitudes are set to 1 and the bus angles are set to zeros, and then calculate the gain matrix g of x k. Now how do you calculate the gain matrix g of x k? We have this gain matrix is nothing but ht r inverse into h. What is r inverse? Basically this is a weighted matrix, weight matrix. I told you each measurement device will be given some weightage based on its previous track record. Now how like let us say 1999 times out of 1000 it is giving a true value, then you will be giving it a very high weight actually. The measurement from that device is considered to be a most accurate measurement. Let us say a specific measurement device which is giving true value 500 times out of 1000, it is 50% weightage basically, right. So that means you are giving less weightage for that specific measurement device. So it depends upon the previous history. So you have this entry already there because you have a lot of data being collected for time, very long time. So you have this is a constant matrix, and you also know what is Hessian matrix that we have already defined. So by knowing this you can find out the gain matrix. So once you have find out the gain matrix, you know what is H, this Hessian matrix, and these are the previous state values, voltage and angle in the previous iteration, and this is a weighted matrix that also you know, and Z minus this is the Z is the actual measurement at this instant. and h of xk is that model, you know, that we have model function that we have discussed, x1 x2 and all these values. So you can now calculate the right hand side of the above equation. So the gain matrix g of xk is decomposed and it is solved for delta xk plus 1. Ultimately you need to find out delta xk plus 1. You know what is g of x, g of xk, you know what is the right hand side, find out what is delta xk plus 1, right. Now if this maximum of this deviation, if it is less than the error, you have some threshold value already predefined, the iteration takes to be converged. Now you assume that it is converged. Now if above is not satisfied, then update x of k plus 1 with xk plus delta xk plus 1, which you have got in the previous iteration. So again you follow the same procedure. So the gain matrix g of xk is rarely inverted directly to avoid numerical problems. Numerically efficient techniques such as Cholesky factorization or Gauss elimination are usually used to decompose the gain matrix. So one example you can see here, this is just a DC power flow, this impedance and phase angles have been given here. You need to find out the phase angle basically. So you have got this power flow, this is a measurement matrix Z, you have this line parameters, with this line parameters you are going to find out that H matrix basically. So you have to find out the state variables theta 1 theta 2, right. So bus 3 is considered as a reference bus, that means this angle is 0, you need to find out phase angles of bus 1 and bus 2 basically, right. So how do you do it? So Z1 Z2 Z, this is the line flow measurement, actual measurement, then that is a dependence matrix, you just, I am just expressing in the matrix form, that is nothing but 1 by x12, that is Z12 is nothing but theta 1 minus theta 2 by x12, phase angle difference divided by reactance. Similarly you get Z13, you will get Z32, right. The objective is to find out theta 1 and theta 2, the states. How do you find out? Again follow the previous procedure, I gave the steps. So find out the gain matrix, Hessian matrix, and you have the measurement matrix, and then by which you will find out the system states. So then reasons for using state estimator, why we are doing state estimation? State estimator can give the value of a line flow that is not measured, and state estimator can tell if one or more measurements are bad, that is detecting and identifying bad measurements. If you suddenly get a value which is true far from the variance, then what would be the actual value? So from previous track record, can you able to find out the possible close value? So there state estimator will help. So some drawback of SCADA based state estimator, the refresh rate of SCADA data is slow, remote terminal units are scanned at every 2 to 5 seconds, the state estimator gives output every 1 to 5 minutes. After running bad data detection, identifying and processing, it takes a lot of time. So it is technically difficult to obtain the voltage phase angles in real time from widely dispersed location with respect to a common reference by using conventional measurements in the state estimator. So basically the synchronization is not so easy, this has different time scale. So real time visualization of the power system is therefore not possible by using this SCADA system, it is not actual real time, it takes a lot of time for the, you get the measurement, then you takes a lot of time for state estimation, check whether the data is true or not, then use that measurement for load flow analysis, this is a long procedure. So real time visualization of power system is very tedious thing. So phasor measurement technology alleviates the above problem. Even you can see here, PMUs can provide measurements at sub-second rate, typically up to 50 and 60 times per second for 50 and 60 hertz systems, compared to 2 to 5 second scan rate of RTUs. So PMUs provide direct measurement of the phase angles, which was technically infeasible so far with the existing SCADA based measurements. Earlier SCADA based measurements would not give you phase angle. This technology offers wide area visibility. This in turn facilitates the capability for distributed sensing and coordinated control action. So controlling would be more faster. So PMUs are typically much more accurate than the conventional SCADA based measurements. So integration of PMUs into state estimator. So the design and deployment of the hybrid state estimator is still in the experimental stage, and the following are some of the benefits that can be derived as a result of including PMU with the state estimator. Improved accuracy of the state estimator because you are getting more samples. So more samples means more accuracy, right? Better observability, enhanced convergence characteristics, better handling of bad data. So PMU based state estimator will be better than SCADA based state estimator. Some source of error in state estimation. The quality of the measurements used in state estimator vary, and the use of a state estimator gives engineers and power system operators a mean to cope with errors. A partial list of error source are as follows: modeling error, data error, transducer error and sampling error. These are the 4 typical errors that one can see. I will just give you a light about each of this. So modeling error. These have to do with the fact that the model of the transmission system may be incorrect. Now you need model, right, the H of X matrix may be incorrect to begin with. Impedance data for transmission lines and transformers can be calculated wrong because there could be wrong in the calculation, or may have drifted due to environmental factors, right. So transmission line may expand, there could be some practical scenarios where there could be different value such as ground moisture and all these things. Finally, modeling errors can be present because breaker and disconnect switch status indications can be wrong due to human error or due to telemetry error through the SCADA system. There could be human error also which may be creating an issue. Telemetry error means the data which is been logged, so that is also there is some issue. So data error, by this are meant the errors that come with incorrect data specifications that indicate which current transformer is connected to which transducer, right, which are the positive and the negative sides of the measurement devices, which breaker status contacts are wired, to which terminal strip connections in the substation building, etc. So these are some of the cases by which you get data error. Sometimes you may connect a measuring device opposite, you instead of getting a positive measurement you may get a negative measurement, you understand, no? Then transducer error. These are errors in the values transmitted from current transformers, potential transformers CT and PT, and transducers that produce signals proportional to P and Q flows, right. These may be simple bias errors that give a constant offset to the measurement value, or they may be random errors giving an error that is distributed around a mean value representing the true measurement value. And there is sampling error. These are due to the fact that SCADA systems do not sample all measurements simultaneously, nor are all the measurements sampled at the same frequency, right. Thus, we are using measurements of time varying quantities that were taken at different times and can be in error simply due to dynamic nature, time changing values of the quantity being measured. Hence, the SCADA based measurement is less accurate compared to PMU, where PMU you get time sample data. So state estimator would be more accurate. So with this we will conclude state estimation and we will consider a new topic. Thank you very much.